my pleasure today to introduce our Colloquium speaker, Dr. Valeria Barra. She did her undergraduate degree in Siena, Italy, and her master's degree, and then got her PhD at the New Jersey Institute of Technology in Newark, New Jersey. And then after that, just went to University of Colorado Boulder, and then continuing to tour all different kinds of climates. New Jersey to Colorado. Is now at Caltech, Pasadena, where she's a fairly new title. This research software engineer is a new title, but as I think many of us in computational science understand, that is a necessity these days. And let's see if there's anything else I want to say. Nope, that's basically everything. So I'll leave it to you.
Okay, thank you so much, Dr. Johnson, for the introduction, and thank you for the invitation. I'm very, very happy to be here. I hope this is loud enough. So yes, this talk pretty much summarizes a lot of my research contributions, not all of them, but a lot of them. My journey in different realms of applied and computational mathematics. So I could subdivide today's talk in three main sections. The first one being the work that I've done in my PhD research, the second one, the one that I've done in my postdoc, and the third one, the one that I'm doing now currently in the current position I'm working now. So let's dive in with my PhD work first. As a PhD, I have a PhD in applied mathematics from NJT, as he mentioned. I worked on numerical simulations of thin films. Sometimes they're also called long wave approximations, specifically for viscoelastic fluids. Why viscoelastic fluids? They are ubiquitous. They're all around us. So first of all, some of our body fluids are viscoelastic. So for instance, blood, mucus, or saliva. Or you can find them in the kitchen or in the bathroom, for instance, shampoo or toothpaste. Or they can be employed in some industrial applications. One of the most common ones is biomedical field. For diagnostic testing, for instance, they use a lot of polymers, and I was looking specifically at polymeric films. Or for instance, another industrial application is inkjet printing. So if you look at this, how this nozzle sprays the ink or paint on the paper sheet, it deposits this very thin layer of fluid on a flat substrate. And this, we're talking about like nanometer scales usually. So this is the type of setting that I was analyzing. So viscoelastic materials behave quite counterintuitively relative to other liquids that we encounter in our everyday life. For instance, water or some viscous fluid like honey. They have three main characteristics in terms of like materials. They present hysteresis, that means a loop in the stress strain curve. They also present stress relaxation. That means that for constant strain, so for constant deformation, you have decreasing stress. That's something that you might have experienced if you ever do stretching. So your muscle will be exposed to a constant deformation. After a while, you'll have relaxation. Creep, on the other hand, is constant stress induces increasing strain. So we know that in continuum mechanics, we can describe the constitutive material relationship or properties of materials via this mechanical system analog. For instance, we know the simplest law for linear elastic solids is the Hookean law. So here we write it in terms of tensional stress, where G is the shear elastic modulus. We know that if we extend the rod, it's typically represented by a spring. A spring is an energy storing device. On the other hand, if we look at the law for Newtonian viscous fluid, we see that the analogies are striking. We have the strain rate in place of the strain, and the viscosity, dynamic shear viscosity coefficient in place of the G shear elastic modulus. But the constitutive relationship really looks similar. And we represent this by a dashpot, which is an energy dissipating device. If you compose these two in parallel, we have what we call the Kelvin-Voigt model, and this is suitable to describe linear viscoelastic solids. And if you compose these two in series, we have what we call the Maxwell model, and this is suitable to describe linear viscoelastic fluids. The constitutive relationship, if we look at it for a second, we have this λ1, which is a characteristic time, and it's called relaxation time. If we switch this off, we see that we go back to the Newtonian case. So this makes it very convenient. The type of fluid that I was analyzing are one step forward in complexity, and they are described via a Maxwell system in parallel with another dashpot. Why we have two dashpots in this system? Because usually these polymeric liquids are compound and they're made via a Newtonian solvent and a polymeric solute. So we now have two viscosity coefficients. One is the one for the solvent and the other one is for the polymeric solute. So this is how the constitutive relationship looks like. It's a non-Newtonian, so it's a complex fluid. It has time derivative of the stress tensor, and now it has also time derivative of the strain rate. So if you want, it's like an acceleration. And now we have two characteristic times. One is called the relaxation time again, and the other one is the retardation time. So, and one is greater than the other by construction. And you might think of two different responses to deformation, so two different times. For instance, if you think of a little bit of mucus or saliva between your fingers, I know it's gross, but if you think of it, extend it, you release it, you first have like a fast response, like an elastic band type of response, elastic response, but then the material will also kind of bound back and forth and kind of settle to the final configuration. So these are the two different characteristic times. In terms of constitutive law, we saw that. In terms of governing equations, we have the conservation laws, typical in fluid dynamics. So the Navier-Stokes equation, where I wrote it here pretty generically. So with the divergence of the stress tensor, where again, the stress tensor follows this Jeffreys model for non-Newtonian model. Here we see, for instance, the body force for forces like gravity, and we have the incompressibility condition. So this is incompressible fluid. So we have constant density. This is a 2D setting, the one that I'm going to analyze here. And you might notice, unlike the usual Navier-Stokes equation where you have the pressure gradient here, delta P, we also have an additional term. This is called disjoining pressure. And this is due to interaction forces. So these are forces that become important at molecular length scales. So these are attraction-repulsion forces between the molecules of the fluid and the molecules of the substrate, the solid substrate. And this is both attraction and repulsion because it is attractive up to a certain length scale, usually molecular length scale, and then it becomes repulsive. So the fluid and the solid will never break. But there's always going to be like a very, very thin layer of separation between the two. Okay, so this is the setup for thin film approximations or long wave approximations. So the aim is to track the interface function in space and time. So we want to track the evolution of the interface and look at what we call interfacial flow and interfacial instabilities. So we have two fluids. So we have the liquid at the bottom, and the one on top is just passive surrounding gas like air in the environment. We have typical boundary conditions here, like the non-penetration boundary condition at the bottom, so no vertical component of velocity. But we do allow some horizontal slippage here. So we have the Navier slip boundary condition where B is the slip coefficient. At the interface, we have important boundary conditions because in this type of problems, we have, these are problems where surface tension matters. So we have the Laplace boundary condition that is the one that describes the jump in pressure at the interface, and this is balanced by the surface tension. We use constant surface tension for this study. Probably the most important boundary condition of all is what we call the kinematic boundary condition. So this describes that at the interface, So the interface function moves with the same velocity as the flow. So this is a key point, because together with the usual trick in physics or applied math is non-dimensionalization. So we scale according to some scaling of interest. In our case, we take advantage of the fact that we have very long waves compared to the very thin height. So we have a small aspect ratio of the height scale over the length scale, and we linearize the equations around this small parameter. And what we do is we end up with one equation only for the interface function h, so the height function. So we started with the Navier-Stokes system, which is two equations in two unknown, pressure and velocity, and we end up with one equation only. The way that I wrote it here is actually I wrote it so that these two auxiliary equations for capital Q and capital R, those are two linear ODEs that can be solved exactly, and they can be plugged in back here. So it is a big, massive equation, but at least it's one equation to solve for the interface. If you've seen thin film approximations or long wave approximations before, you might recognize some typical feature. But the innovation or the novelty of my study was to include all of these different physical parameters. For instance, there was no prior numerical study that included both the slippage with the substrate and the van der Waals interaction. Some typical features I was saying is, for instance, you have a fourth order spatial derivative. You have here nonlinearities. These are due to capillarity. But some atypical features due to viscoelasticity in this case are the second order time derivative and the mixed time and space derivative. So, and this is the form of the disjoining pressure that we use that allows us to control the precursor thin layer film thickness, which is the one that I was saying. We analyze setting in which, let me just go back to the setup. We are going to analyze settings in which this interface function is unstable. And we're going to look at what we call de-wetting phenomena, or wetting. So de-wetting is when the fluid spontaneously separates in different blobs of fluid and exposes the substrate. But we have to think that this interface mathematically is a continuous function, so it will never completely expose the substrate 100%, but there's always going to be a very, very thin layer there. And that's controlled by this parameter, h sub star. And then we have the contact angle between the interface and the solid substrate, which is also controlled by this parameter. So some examples of this is the evolution of an interface. It starts flat, we give it a sinusoidal perturbation, and this continuously evolves due to the van der Waals force. There's no gravity here, it's just the van der Waals that does the attraction. And then the film separates into these separate rims. And when it's fully separated, we say that it's fully developed. And one of the innovations in my study was that we were able to obtain this satellite droplet in between. And this were a novelty, but we were able to confirm this in experimental findings. So they're observed in experimental settings. But these are due to viscoelasticity because they're not present in the Newtonian case, in the viscous case. Other example, for instance, of different settings, here I consider slip coefficients to see how the slippage affects. And we saw that the slippage affects not only the dynamic, but also the final morphology. In fact, here we have the blue curve, which is the one with slippage, has already fully developed, where the red one is the one without slippage, is still behind and it's developing, and it has all of these satellite droplets that the blue one doesn't. On the right panel here, you see an example of an inverted plane. So now we do have also gravity competing effect with interaction force. And now we have analyzing the Rayleigh-Taylor instability. So now the fluid is on top and the air is at the bottom. Another setting that I analyzed was the spreading and receding of drops. And here I could see that the viscoelastic drop spreads faster and recedes slower. And I could track the contact line angle here. And I could verify that there is a law that is called Cox-Barnett law that determines the contact angle. It is valid for Newtonian, but not for non-Newtonian. A secondary project in my PhD that I wanted to undertake, and I did undertake at the end of my PhD in my last year. It was on membranes. So specifically, this was a secondary project that I designed so that I could use a finite element formulation, because the previous code was staggered finite differences. I wanted to learn finite element and get more experience, so I chose this project for viscoelastic membranes, and we analyzed different types of free boundary flows. For instance, the shear flow on the left and extensional flow on the right. This also has like industrial applications. For instance, the one on the right, the extensional, it's the drawing or redrawing processes with which people manufacture fiber optic materials. So this line of research led to 3 first order publications for me as a PhD student. And also more recently, I was contacted by Bamikole Adeyemi, a PhD student at the University of Aberdeen in Scotland, who really wanted to extend my work. And he wanted to include different effects, like the surface tension gradients, so to analyze the Marangoni effect. So I helped him a lot, and I ended up collaborating and supervising him. So here is his publication where I was given the last author to reflect my supervising role. Okay, this is something that I don't think I'm gonna actually properly discuss. I also had an industry experience. I think in the interest of time, I'm going to skip these slides, but especially if students are interested at the end, we can come back to it and you can ask questions. So I'm going to skip the industry slide, and this is a good place for me to pause if you have any questions.
I was wondering, this may be a very simple question or something, but in the examples that you showed about the fluid parting and the left dry surface.
Yes.
And then at the bottom,
yes,
we saw like in the last, the next slide.
Oh, yes.
Maybe like right there. And so at the bottom where it's dry, quote unquote,
yes,
there's an oscillatory phenomenon.
So those are
Is
the
that real? Is that a mathematical artifact?
Yeah, so those are definitely not a numerical or mathematical artifacts because they persist after great refinements, and I did all of those convergence studies. They are explained physically, and we could explain them and validate with experimental studies, because these molecules, you have to think these are polymeric molecules, so these are very long chains of molecules and they're very entangled. So here, what we could explain is that the case with no slippage has more entanglement, whereas when we introduce slippage with the substrate, this entanglement is kind of like, they're kind of like those molecules are washed away in a sense. So there's no, that's why there's no satellite droplets there.
Oh.
But yeah, the resolution that I was using here might kind of see like these are oscillations, but if you look at the previous, it's definitely, you can see that these are not very, very close, and they are persistent to equilibrium. This is equilibrium state. You can let this run forever. They're persistent. Yeah, so these are nonlinearities.
It's probably way too simple or unfair to say that that's like a micro expression of the gross phenomena of the fluid separating.
We don't,
probably not true.
I don't know if, like,
different.
I don't know to confirm that because it does not happen in the Newtonian case, which has the same separation of the rims and the same phenomenon. It just does not present those.
Okay.
So those are definitely induced by viscoelasticity. Yeah, that's what we found.
And how does the resolution of your mesh?
Yeah.
How does it affect the algorithm?
We did several studies with several different resolutions, and they're all persistent. So they were not dependent on the, of course, we were able to fully resolve this with the grid size chosen. So of course, we saw that they're not affected by the grid size.
If you increase the grid size, it's possible.
Oh, yeah. Yes, if you increase, of course, you're not resolving. Yes.
Oh, I have a question related with the surface tension, because of course it depends on the size of your experiment in which how the surface tension will be super important or not important at all. In your simulation, you are dealing with a situation in which the surface tension is important as well.
Yes, and we use this scaling for the surface tension parameter here.
Yep.
So it is quite important if you think that epsilon is a small parameter. So usually for the aspect ratio that I was running, epsilon could be 0.01, for instance.
Okay. And with the long way approximation that you are using, you are not missing anything which can be maybe the real physics important compared to
Well,
van der Waals and other phenomena.
not in this setting. But of course, these are problems where you have moderate to small Reynolds number. So of course, you don't really have much importance on like inertial effects. So yeah. Okay. I think I can move on to the next part. So the next part is my postdoc project. So for my postdoc, I was part of a very large collaborative consortium project. I was at the University of Colorado at Boulder, supervised by Jed Brown, and our project was really a multi-institution consortium project between several national labs and universities. So actually, I didn't put all of the logos here, but it was the PI of the project. The project is called SEED, Center for Efficient Exascale Discretization. The PI is Sanyo Kolev at Livermore National Lab, and we also work very closely with Argonne National Lab and Oak Ridge National Lab, and universities like Virginia Tech, University of Tennessee, RPI, and UIUC. We were under the umbrella of the Exascale Computing Project, so big DOE funding. And the main motivation behind our work was to provide efficient mathematical software libraries to be able to fully exploit the upcoming exascale machines from DOE facilities. So my motto has always been, what's the point of having a Ferrari if you drive it stuck in second gear? So we were helping in providing efficient mathematical software libraries to run those machines at best and to fully exploit them. And the way we were doing that is by employing matrix-free methods, especially targeting high-order finite element or spectral element methods, because they are very efficient. So let me give you a motivation why high-order methods. So historically, high-order methods have been considered too computationally expensive, especially for industry standards. So they haven't really been used historically because they rely on the assembly of sparse matrices. And when you assemble a sparse matrix, results to P to the D storage and P to the 2D compute per degree of freedom, DOF, in D dimension for basis polynomial order P. But on the other hand, if you avoid assembling your matrix and you use what is called matrix-free representation, and if you're smart about your implementation by using things like tensor product elements and tensor contractions, you really significantly reduce and you can achieve order 1 storage and order P compute per degree of freedom. So here a graph that shows you two different panels. On the right panel, we have a performance model that was probably relevant up to a couple of decades ago. So where the y-axis here, we measure flops per degrees of freedom. So floating point operation per degrees of freedom. On the x-axis, we have polynomial order, and we compare the cost of assembling a matrix versus non-assembling, so the matrix free. And here we see that assembling the matrix, the brown and green curve, can kind of still make sense if you're a very low order, 1 and 2. But this performance model is not relevant nowadays when we know that Moore's law is dead and we know that performance bottleneck is not processor clock speed anymore, but it is memory bandwidth. So we look at the left panel here where the y-axis is bytes per degree of freedom. So in here, we see that assembling the matrix never makes sense because the cost just skyrockets. And you actually see that for matrix-free methods, the higher the order, the better it is in terms of memory bandwidth. So the main motivation is why not use high order methods when you know that they're more efficient on modern architectures. They give you all the nicest properties because by definition, they give you faster convergence and higher accuracy. So libseed is the library of the Center for Efficient Extensible Discretization. It's an open source library that targets matrix-free operator, especially for high order spectral element methods, but not only, especially for tensor product structures, but not only. And it's a purely algebraic, it has a purely algebraic interface. That means that the user can easily adopt libseed in existing legacy code, but also in new code. It's an open source project, so you can find it on GitHub, and it's a C library with Fortran, Python, Julia, and Rust interfaces. And it's very lightweight and achieves performance portability via runtime selection of specialized implementations that we call backend. And this can be optimized for CPUs and GPUs. So for instance, here you see a schematic of the role of libseed, especially in the scientific computing ecosystem, like with, you might have an application, for instance, in MFEM, which is a pretty popular package in the finite element community, or NEC 5000, pretty popular in the CFD community, or PETSI, Portable Extensible Toolkit for Scientific Computation. This can call libseed as a low-layer, low-level library, which in turn uses all of its internal backends that are fine-tuned and specialized to run on CPUs, GPUs, or some of them, like the Alka backend, runs on both CPUs and GPUs. And these are selectable at runtime. So we're not asking the user to change so much of their code. When they make a commitment, then they can change and select at runtime whether they want to run on a GPU or a CPU. Some performance plots here. So here we're comparing our best performance CPU backend on the left with our best performance GPU backend on the right. And these are plots where on the x-axis we have time for conjugate gradient iteration. So these are typical benchmark problems in the HPC community. This is a Poisson problem. So it's a Laplace operator in 3D. And on the y-axis, we measure efficiency in terms of mega degrees of freedom per second per conjugate gradient iteration. And we see here different nodes, and this corresponds to problem sizes, so problem dimension. To the far right of the graph, we have million degrees of freedom. And of course, we would like this curve to be as straight as possible and as pushed to the left as possible. We see that the CPU backend has a peak performance and then it kind of degrades, and that's because of cache spills. Whereas we see the GPU backend here is the one that performs at best when loaded at best. So we see that we reach almost 3 gigaflops per second. So before joining this project, I was not a performance engineer. So because of my background in applied mathematics, especially with applications in fluid dynamics and solid continuum mechanics, I didn't really work so much on the back end, also because they were already developed by the time I joined. So I worked more at the front end of the library. So I developed application examples of what we call mini apps. So in particular, I worked on 2 mini apps, one for fluids and one for solid mechanics of hyperelastic materials. And I pretty much set the foundations for these mini apps that then the students and the group pursued even further. So, and these are mini apps that are integrated as PETSI examples, so PETSI applications. So here on the left, we see an example of DNS, direct numerical simulations of a flat plate synthetic turbulence generator that the students worked on. And here on the right, we have a compressed Schwartz periodic minimal surface. This has applications in additive manufacturing and soft robotics. So while I was there as a postdoc, I co-mentored some of the students. For instance, here, Jose was an undergraduate research program for a student. And Jeremy, one of the PhD students and main developer of the library, who also stayed with the group after graduation as a research software engineer, and Leila, another PhD student, This is a paper that we have in preparation with the group where we show that our solid mechanics mini app performs orders of magnitude better than commercial software in continuum mechanics to achieve the same engineering tolerances at a fraction of the cost. Other collaborative publications in my postdoc. Some of them I could not write all of the others because they're really, it's a very large collaborative project. So like this publication in the International Journal of High Performance Computing Applications has something like 30 others for 14 different institutions.
Wow.
So I couldn't write them down here. Then here, the JAWS publication, the Journal Open Source Software. So if you want to check out LibSeed and its API, it will be here in the JAWS paper. And here, the one that I led is about the Python interface because I developed the C Python interface for this library. Okay, so this is another good place to pause if you have any questions.
There's an observation that in this case, the first author is not a student.
Exactly. It was a decision between the co-PIs of the project. Yeah. But this one was alphabetical, the parallel computing one. And I have a B, so. Okay, so next to the current project. I work with CLIMA. CLIMA is yet another large collaborative consortium project now between Caltech, MIT, and NASA JPL. We also used to work with NPS in Monterey. CLIMA is a coalition of scientists, engineers, and applied mathematicians like me who are trying to build the first Earth system model. So it's a climate model entirely written in the Julia high-level programming language. And this model wants to learn from diverse data sources that can be observationals or also computational to produce more accurate climate predictions with quantified uncertainty. So here's a picture of a recent project meeting. So if you haven't heard of an Earth system model, it's okay because I also was not in the geophysics applications before. This is a schematic of what an Earth system model is. So we're trying to simulate the entire Earth as a system. So you might imagine the Earth is a very complex system. It has multi-physics components to it. It has multiple scales. So you can see this schematic of how you want to subdivide different components of the Earth system model. We have, for instance, the ocean component, which is entirely developed at MIT by our collaborators. They work on this package that they call Oceananigan. And then we have the atmosphere component that is entirely developed at Caltech. And then the land component, which is the one that describes the land hydrology, rivers, and other basins of waters, is in collaboration between Caltech and NASA JPL. And then we also have some other link components. For instance, the land biosphere is basically the one that communicates quantities between the land and the atmosphere. So if you think of tree canopy, they exchange carbon dioxide and other quantities. We also have ocean biosphere, and then we will have sea ice and land ice. Where I work in this, I work mainly in the atmosphere and also mainly in the core. So what we call the DI core. So it's the dynamical core, meaning the library, again, mathematical tools to describe the partial differential equations needed, so the governing equations. And the core that I work on is able to describe both the atmosphere and the land equations. So it has to be pretty flexible. So one of the aims of CLIMA is to build this Earth system model that will be grounded in physics. So it will use subgrid scale cloud resolving modeling, but it will also be designed for automatic calibrations of parameters via machine learning, which is not an area of research that I work on personally. We have a dedicated team of ML and data simulation people. And also the other main goal is that we want to support both large eddy simulations and global circulation models. So large eddy simulation, you think of a computational cell, which is like a box. So it's like a Cartesian box. And since it's a limited domain, you can run very high resolution studies, and those can be cloud resolving. But you can imagine that you can now run such a very high resolution at cloud resolving scale with all the microphysical processes happening on a global scale, because that would become computationally so expensive and unfeasible. And that would also create, probably, even if you were able to do that, it would probably create such a carbon footprint that we don't want to, right? So we're trying to solve the problem here, not to create a new one. So what we do is bridging this scale gap. So by using the large eddy simulations that are used to inform the parameterization of the global circulation model, which in turn can be used for large-scale forcings to force the LEF. So this is how you bridge the scale gap between these different scales. Okay, so we have some technical and scientific aims. So as a code base, we want to support both CPUs and GPUs using a common open source code written again in the high-level dynamic language Julia. Similar syntax to Python and MATLAB, if you've ever seen those, but it could be also very efficient. Julia has an interactive REPL, so it has a very nice user experience for debugging, especially you can check the variable space very easily. Julia uses just-in-time compilations that is triggered by the first evaluation of the function. Julia allows polymorphism, but in a very different way from, for instance, all other languages that you might be familiar with, like object-oriented, like C++. Julia allows polymorphism via what they call multiple dispatch. And this dispatch can run compile time or runtime, and it will specialize on the type of calling argument. So for instance, you can write a pretty generic code like a function f of an argument x. This x can be labeled as an abstract array, and initially the compiler doesn't need to know what that is. It could be an array of floats, like double precision, half precision. It could be also a CUDA array. So it will specialize. And if it's a CUDA array, it will launch a dedicated CUDA kernel. So this makes it very accessible and extensible by a mixture of users, and also makes it very attractive, especially for young talent. We attract so many young students because we're using Julia right now. For the atmosphere model, we want to support both large eddy simulations and general circulation configurations. So that translates geometrically into supporting both Cartesian and curvilinear meshes. We want to allow specification of any governing equations and boundary conditions and composing the operators. And we want to support non-uniform structural meshes. So there was a first iteration, the first code base, Climate Machine, developed in particular in collaboration with NPF, which supported only discontinuous Galerkin discretization, and it supported only the specification of the PDA in conservation form. It was successful and was very scalable, but it was also a bit inflexible, let's say. So this used kernel abstractions.jl, which is a package for unified programming model, similar to OpenCL and SQL. So it allows for single source code for CPUs and GPUs. But it was primarily, quote unquote, a GPU code which also ran on CPU. It overlapped computation communication using distribution via npi.jl, which is the NPI Julia wrapper. It was very efficient, as I mentioned, but it was somewhat inflexible. So this is a paper that my colleagues worked on even before I even joined. This is another paper. The first one was on the LEF configuration only. The second one by my colleague Andres Souza at MIT is on the GCM configuration and is currently under review in Jane. Okay, so we wanted to have something more flexible. Especially, we wanted to support both the atmosphere and the land component. So these are different components that have different needs. Especially, we also wanted to support staggered grids, which are useful in the atmosphere. So we started a new code base. So now the new DICOR is called climacore.jl. So it's a library set of tools for constructing flexible space discretization. So this is where I've been working the most in. So for this geometry, we support both Cartesian and curvilinear spherical geometries. And for this, we need to support different vector basis representations. So we have Cartesian and covariant, contravariant, but those have a unified interface, so the user doesn't need to worry when they define a vector or a vector field. They don't need to worry if it's a straight grid or if it's a curvilinear grid. And as for space discretizations, we support now in the horizontal direction both continuous Galerkin and discontinuous Galerkin, but we really use CG, continuous now. And in the vertical direction, we have staggered finite differences, where the way we staggered quantities is at cell faces, we define vertical velocities, and at cell centers, we define horizontal velocities and all the scalar quantities like density, tracers, and energy. Okay, so this is just an overview of the API. Very quickly, we have different objects in this hierarchical order. So the domain is the one where you define your bounding box, basically. It could be a rectangle or a circle. Then the mesh is the one that knows about the resolution. Topology is the one that knows about orientation of vertices and edges. And space is the one where you define if you want to have a finite element space. So it will define the nodes, or if you want to have a finite difference space. And then the field is really the concept of a mathematical field. So it could be a scalar valued field or a vector valued field. And you define this in this hierarchical order. So we could have also, there are some other packages out there where all of this is glued in one object and you say like create space, for instance. But we wanted to separate this, especially because in HP refinement studies, it is useful to have separation between mesh resolution and element polynomial degree. So here is a snippet of our code. So how I would define each of these objects. And once you have a space, you can define the field, as I mentioned, is a mathematical field. Field stores the values of the geometry and mesh info at the nodal values. And it has some useful overloads, for instance, sum to compute integrals, norm, and mean. So here you have an example of sum of a field of 1, so it's just a vector of 1 on the space. So this would give me, in one line, the surface area integral of this space. So as I mentioned, we support now flexible data layouts. So we support array of structs of arrays and of combinations. We have a common interface for instructing 2D data and 1D data. We allow element node size dimension to the type domain so that we can specialize on polynomial degree. This is very useful for loop unrolling, so for vectorized instructions and also kernel performance. We have memory flexible, flexible memory layouts for allowing for flexible threading models. So on CPU, for instance, we would process batches of horizontal elements at a time. On GPUs, we would thread over nodes or node columns. And currently, the GPU work is ongoing in our group. So a little bit about Julia. If you're not familiar with Julia and Julia broadcasting, you might be familiar with the MATLAB syntax of the dot operator. So if you've seen MATLAB, you know, if a function f is applied with a dot to an array or a collection or a vector, you know that you're applying that function or operator to the entire collection, right? So to all entries of that array. In Julia, you can fuse multiple operators and assign to an existing array without the need for temporaries. So you don't need to store any intermediate memory. So for instance, here in this instruction, we have this will be translated internally in Julia calls like this. We would have the first call, which is broadcast f over the array f, which is f.x here. Then the result of this is broadcasted with epsilon and the times operator. The result of this is broadcasted with x naught and the plus operator. All of this, you assign it to an existing array y, all without needing temporary. The only time where the compiler iterates over the array data is in the materialize function. That's the only time. So by extending this, we can also compose our differential operators. So we have this user extensible API where we can write a custom function and differential operators. For instance, here you see an example of a gradient and a weak divergence, and you can compose the two to make a Laplacian. So here you have a weak divergence of grad u, which is Laplace u. And this again will not need any temporaries. So again, it's a user extensible API where it's specialized on argument types. So if it's a CUDA array, the compiler would apply a custom CUDA kernel. These are pseudo functions, and again, this is a matrix-free operator representation, so we're not assembling any sparse matrix. Okay, so we only specify the action here of the physical operator. Some personal contributions that I've been involved with. I particularly care about education and providing educational material. So I was the creator of a lot of our documentation, tutorials, and I created this series of workshops that it's called Klima Workshops, and they're all freely available on our GitHub page, so you can check it out. I work extensively in unit testing, integration testing, and examples, and I always strive for best practices and good quality of code. I work in some high-order differential operators and flux limiters, where I'm going to dig in a bit more in the next few slides. We support different cube spheres, so I work on mass generation. We support equiangular, equidistant, and conformal. They all have some different pros and cons according to the needs. So for the atmosphere, we use the equiangular. For the ocean model, they use the conformal. So you have to do some remapping or regrading when you treat quantities at the interface. Some example. So for instance, I worked on the suite of shallow water equation solver. So if we look here on the top left, we have the shallow water equations in vector invariant form. And here on the right, we have it in terms when expressed in terms of curvilinear basis. So in the curvilinear basis, you will have this Jacobian popping out of the divergence operator, and the covariant, contravariant basis, they get a bit messy. But with our unified interface, this is how this translates in Julia code. And Julia is really nice because it allows you to use Unicode characters. So it's also very easy to read. So here is how we only need to define 3 operators to define the shallow water equations, which are these 2 lines. So they really translate. You can really read the code and look at the math, and you can really see the one-to-one correspondence here. So we look at the divergence of H times U for the continuity equation here, and we look at this other term, which really corresponds to this like norm square here and the curve here. And so these are examples. These are typical test cases used in the atmosphere. So these are known in the literature. They're used for validation of our code. So on the left, we have what is called a mountain test case, where we have a non-uniform mountain here. And on the right, it's the test case that it's called barotropic instability, where it creates this highly vertical structure. Other aspect that I worked on is transport problems, especially lately. So for instance, if we look at this transport problem where we have this quantity, capital Q, which is advected by the velocity u, and capital Q is defined as rho times little q, where little q denotes the tracer concentration. So this could be like the mixing ratio, or it could be mass of tracers per mass of dry air in dry problems, or mass of tracers per mass of moist air in moist problems. So again, how we define this in our interface, it will be just these 2 very simple 2 lines, and it really looks like the math. But we may have some problems because we use spectral element methods, and we know that the spectral element advection operator can be oscillatory, especially at high orders, because we know Eddying and Gibbs phenomenon effects. But we also know that it has some nice mimetic properties, like it's locally conservative, and it has a monotone property with respect to element averages. So Guba and colleagues in 2014 developed this class of what are called optimization-based limiters. So these are a class of conservative quasi-monotone limiters, meaning quasi-monotone means monotone with respect to the nodal values in this case. And they are used to prevent undesired oscillations, so undesired overshoots and undershoots of the tracer quantity. It maintains quasi-monotonicity also if you add dissipation like viscosity or hyperviscosity to the problem. Involves solving a constraint optimization problem for each element. So it's a weighted least square problem that is, so for each problem you solve a quadratic program. So that is a quadratic objective function subject to a linear constraint. The only additional inter-element communication that it adds is to determine the bounds, so the mean and max that you want to have constraint value within. So some examples here. For instance, on the left panel we have advection. This is a typical test case. It's a slotted cylinder, so it has these sharp features on purpose. And we let it run. This is just advection. There's no diffusion in the problem. And we see how this, without the limiter, creates those ripples on the left. So these are undesired numerical artifacts. And on the right, it is very smooth. So problem solved. And this is a 6-degree polynomial, so it's a pretty high order. So that's why you see all of those ripples here. Another aspect that I focused on in the last period is flux correlated transport. So we use this in our vertical discretization. So remember I said in the vertical we use staggered finite differences. So in this case, the vertical velocity lives at cell faces. The scalar tracer lives at cell centers. So you have to do some sort of reconstruction to advect this quantity. We do like high order reconstruction. But again, there was a proposed method to overcome some of these challenges. Boris and Book in 1973, and then later Zalezak in 1979, they proposed this model so that you have a combination of high order upwinding where the solution is smooth with a combination of low order upwinding where the solution is poorly resolved or discontinuous. So here is a nice example. On the leftmost panel, we have a first order upwinding of a square wave or pulse. The blue is the approximated solution, the red is the analytical solution. And we see how the first order upwinding produces a pretty dispersive solution. So the wave has significantly shifted laterally. On the other hand, in the middle, we have third order upwinding, which produces these undesired overshoots and undershoots. So this is less dispersive, but it's also less dissipative. Zalezak is the one here on the rightmost panel, which uses this combination of first order and third order upwinding, significantly reduces the lateral dispersion and reduces or gets rid of completely of those undershoots and overshoots. Okay. Some performance optimization efforts in our group. So we always have mathematical numerical optimization. So in the time stepping, for instance, we use strong stability preserving to overcome stringent CFL conditions. We have some Julia optimizations always, so we can disable bound checking to facilitate vectorized CMD instructions. We can use external libraries to ensure type safety, and with that comes compiler type inference. For profiling, we can always make sure that we're targeting our performance. We have a performance CI in addition to like the one that checks for the physical correctness. This is very preliminary scaling results. So in the climate community, they like to measure things in terms of simulated years per day. And this is how much we get up to 512 cores. So right now we get a little over 3 simulated years per day at the target resolution that we're interested in. Our group developed this library that supports generic distributed and shared computing paradigms. And then again, we support CUDA for NVIDIA GPUs. So this concludes the part about the cleanup project. Here are 2 videos that I just want to leave you with. The top one is the health Suarez simulations, which is a typical test case again in the atmosphere, run up to 180 days. And the one here at the bottom is the coupled, you see the entire atmosphere coupled with land and ocean, but ocean here is just surface, it's prescribed sea surface temperature. So this is called AMIP in the climate community. So I showed you ClimaCore API. It's the new DICOR for the CLIMA proposed Earth system model. I introduce some examples and I show you the flexible discretizations and composable solvers for fast solutions. And I showed you examples to overcome challenges in the spectral animal representations like flux limiters and flux covalent transport. These are all thank you to my collaborators and sponsors. And at last, here is the outlook of what I would like to do to establish my own research program. I would like to explore some stabilization methods, in particular, a class of method that is called streamline affine Petrov-Galerkin, SUPG. These methods have been successfully employed in the aerospace engineering community, but they haven't really been explored enough in the numerical weather and climate prediction community. So I would like to explore these methods because they're important because they ensure correct energy behavior, conservation, and stability. So we started this collaboration with Ken Jensen at SU Boulder, who is a pioneer in the SUPG community in the aerospace engineering. And I would like to extend that. Another class of work or stream of work that I started in collaboration with, again, SU Boulder was matrix-free p-multigrid method. In this case, it was for the solid mechanics media that I showed earlier. But I would like to extend these solvers for the class of problems in fluids where this could be beneficial. Last but not the least, I'm always very committed and engaged about mentoring. So here are some of my mentoring experiences. I've served as a mentor for the graduate student math modeling camp, which is a week-long intense workshop for graduate students in mathematical sciences and related disciplines at the University of Delaware for a couple of years. I'm always an advocate for several themes that are very important to me. For instance, representations of underrepresented minorities in STEM, so that might include women in STEM or disabilities in STEM. I always strive for student professional development, and I would be very happy to share all of the resources and all of the professional associations that help me. And I'm also involved with industry and industrial workshops. So thank you so much for your attention. I'll be happy to take any questions.
Yes. So I have some questions about the numeric. You said something about DG wasn't acceptable.
I'm sorry.
You said that DG wasn't.
Oh, not the DG, the code base.
Oh, the code base is not
Yeah.
Now you're using CG also.
Yeah, we're using CG now. Yeah, but
Are you doing either or are you doing?
so initially we started with the idea that we could do either or, and we could allow for both. So our interface does allow for both. In practice, right now we're using CG.
And then for stability, are you using the limiter for stability?
Yeah,
or-
so the limiters that I showed here, the flux limiters for tracers, especially important for moist problems. Those are the ones to, ensure the that you get rid of those undesired like overshoots and undershoots, because otherwise you might end up with negative moisture and you don't want that.
But you're not using any stable formulation.
No, it's just a typical, well, we do have, we use the usual like weak form, and we have equations in conservation form.
But they're not in stable.
No, and exactly the class of methods that I would like to work on in the future, the SUPG methods, they provide energy stability. And one of the studies that I have in mind is a comparative study where I can compare the influence of SUPG and, for instance, entropy stable DG.
Which in the shallow water case is the same thing as energy. Okay.
Yeah, but the work that Andre has in review for James is the one that used the flux differencing entropy stable. This is the one that is currently under review with James. Yeah.
I thought there was some interest in switching that. I don't really think the primary frame.
Yeah, I know that.
Do they have interest in doing stable formulation?
Yeah,
Curious what that would be.
so yeah, there is definitely a recent interest, especially in the DG community, yes, to do entropy stable. Mhm.
By the way, excellent talk, especially covering wide range of things. Yeah, I really appreciate that. My question is very naive question actually. So in that whole climate, whole Earth modeling, it sounds cool that you input everything, but putting everything creates more uncertainty. I was just curious that how much reality actually you have put. Do you have something to test with the data? How much reality? Like even just seeing air is not enough, right? The air
So
in one place is widely heterogeneous. It is especially heterogeneous
Absolutely,
across the world. So how much do you actually put it and how convenient?
So we always use data simulation for both. It could be like computational data, for instance, in this case, where we combine the large eddy simulations with the global model. In this case, it will be artificial computational data. So you run, let's say, 100 of the LES configurations to inform the global model. But we also might use observational data, and we incorporate that with, machine learning for automatic calibrations of parameters. So yeah.
Like a very expensive proposition, because in the data simulation, exactly, that's what I think machine learning may help.
Yeah.
I'm curious, you went over the Pixar stuff.
Yeah, if you want, I can go back just for a little bit. It was just 2 slides. I did an industry experience as a PhD student. I really wanted to work at Pixar because before that, as a master's student, my thesis was in computational geometry for computer graphics applications. So I was really fascinated by the fact that what I was studying in the books was really employed by companies to make visual effects and make movies. And, I thought it was really cool. So I had this dream of mine, which was working at Pixar, and I made it come true at the 4th year of my PhD project, where I worked on, again, fluid simulations, but this time on complex curved surfaces. So I developed 2 proprietary libraries for Pixar in C++. The one here on the left shows, for instance, fluid structure interaction problem. So we have the fluid that goes around this solid obstacle on the sphere, and the user here could select at runtime the obstacles that they wanted to select on the mesh. On the right here, you have a simulation. So this was a Navier-Stokes solver on 2D surfaces. So we could take advantage of the 2D and use the vorticity formulation of the Navier-Stokes. And here you have a mesh with mixed elements. So we have polygons, pentagons. And for this project, I used discrete exterior calculus. So you have all the nice mimetic properties in a finite volume discretization. And I can swear this looks like bleeding, but no animal was hurt in this experiment. The next one was thin films approximation, now on curved surfaces. So similar to what I was doing in the PhD, but on curved surfaces. Here you might see an example of what it might look like a chocolate truffle, if you want. It's some layer that flows down this surface. And here, like a glazed donut on the right. These 2 libraries were developed as plugins for the 3D graphics software package called Houdini that they use in the industry a lot. So overall, yes, it was a very positive experience. I'm still in touch with my mentor at Pixar. They just won an Oscar like last month. They won a technical Oscar for some work that they've done in the fluid simulations in the industry.
And from your website, I just came to know that you are a hip hop dancer.
I was a hip hop.
So when you were in the picture, did you think that's like a connecting the dots kind of things? So your dancing move, you're going to put it in something animation. Did you feel that way?
I saw at some point, I saw that they do employ dancers for motion capture. So, when you're filled with sensors and they do that, I didn't think I could do that. I was there for doing math, but yes, I thought about it at some point. Yeah, but thanks for asking questions.
Well, I had a question. So you were talking about Julia broadcast.
Yeah.
So that's at a high level function, but we're going to be on exascale machines broadcast is not a simple thing, it's going to depend upon machine learning. So that because we're trying to actually not that reduction, and the speed of the reduction varies widely depending upon what our architecture machine. So whose job is it to tune the Julia broadcast, those kind of functions?
So for us, it really depends on, so since we use this differential operator, and here you only assemble how big of a horizontal element you have. So if we have, let's say we run with polynomial order 4, you have a 5 by 5. That's all you assemble. That's much for one element. We have different strategies for threading. So for instance, for CPUs, we thread over elements like horizontal elements. So we have batches of elements. And of course, you want to be careful because you want to try also to, match register sizes. For GPUs, we will thread over nodes in a vertical because we distribute only horizontally in the atmosphere, and for the GPU instead. So if this answers your question, I mean, we allow for different strategies, but it really depends on how big of a problem, how high of a polynomial order you want to run. And yes, you have to be very careful if you're running on a CPU to find that sweet spot according to your problem size. Or if you're running on a GPU, for instance, we're considering annotating entire expressions. So you might annotate an entire expression or a block like these two expressions for like a CUDA kernel, for instance. So instead of the single operator.
So my understanding is, so basically because you're relatively local, that could be local, but
Yeah.
that you think that's the problem, that's not gonna be a big problem. What are you going to do with boundaries? I mean,
Yeah.
can you really, because at some point,
Yeah.
this thing is going to be here, and then the
Yeah.
next cell is on
Right.
the far edge of the
Right.
machine. And that's what's
So
slowing
we
down.
always try to overlap communication and computation as much as we can with MPI. So yes, at some point you will have some ghost cells that need to be shared between the domain decomposition. That's how it happens. So that's unavoidable, I would say. But of course, we need to be careful about load balancing and have the best optimal, balancing, as always. Yeah.
Is Julia a Python derivative?
No, it's really a brand new language. It was developed 10 years ago at MIT in the lab that is now called the Julia Lab. And it does not rely on Python, but it uses the LLVM compiler.
So it's a supposedly a very fast,
Yeah.
but similar to Python.
It has a very nice high-level interface, exactly like dynamic language like Python and MATLAB, but it's supposed to achieve very high performance like Fortran and C.
Okay, so it's
the best of both worlds right now.
So does it rely on Fortran libraries?
No.
So it's being positioned as a replacement for Fortran.
It's the promise for the future of high-performance scientific computing, let's put it that way, that a lot of people are excited about. And we are in Klima, the very first large project that is actually using Julia in a production code. So there's no other comparable large size project like us. So in a way, we have a lot of eyes on us. Because in a way, if we succeed to prove that Julia is really feasible for high performance computing, then a lot of projects might follow.
I will use a wrapper, a Julia wrapper to run.
There are a lot of projects and existing libraries that use Julia wrappers, like Petsy also has a Julia wrapper. A lot of people are getting excited, especially people in the inverse problem adjoint community. Because Julia right now offers the best package for AD, automatic differentiation. It's called Enzyme. It's really the best package out there for AD. So a lot of people are getting excited about.
Other questions? Are there any questions online? Okay, well, then let's thank you.